Okay, so today's class is actually last time we did something kind of complicated. We did Lavat's local lemma. We did the proof. Today's class is actually kind of easy. So easy that I'm already even queued up the next lecture in case we have time. No, we could do that. That's true. Um, so it's something. It's about counting or about sampling. This is a topic I definitely could have done beginning of the semester or something, and I just didn't. So let's take. Okay, let's say that you're very lazy. You're not going to do anything too analytical. How would you estimate the circle area of a circle on a computer if you didn't know that it's equal to r squared, or if I gave you a more exotic shape? Well, sure. Yeah. What would be like an algorithm? Okay, so the suggestion was uh pretty simple. Okay. Uh say it's the unit circle. Let's just draw the bounding square around it, the 2 by 2 square, technically, right? And then just randomly draw points, right? So what's the probability that the point lies in the circle? It would be something like pi over 4. I mean, more slowly, right? It's whatever the area of the circle is divided by the area of the square, which we kind of know is something like 0.785 or something like this, right? So if you just estimate and you take the average over time, it should converge to the true area of the circle. Of course, circle, you already knew the area, but the point is you can do this for other shapes. Okay. Um, good. Now, how would we analyze our algorithm, right? We actually want to know over case samples what my accuracy looks like or something like this. What tools would we use? How would we apply it? Oh, actually, yeah, you could do much. Oh, no, you don't need to do epsilon sampling. Epsilon sample is about trying to satisfy many shapes at once. Here, you're only down to one shape, so it's not that big a deal. Oh, yeah, so you might use the turn-off bound. So what would be the appropriate indicator variables? Amazing. Okay, so we set up indicator variables, right? Just say whether it's in the circle or not. Okay, and uh, and then you might say, okay, what are the odds that I'm off by 5% or something, right? So you're gonna sample this. I guess this n should probably be a k, but you'll sample this k times, and you'll just take the average and hope that's close to your true probability p. Okay, and remember what this roughly is. Or actually, you don't have to remember. Okay, it'll be something like this. Okay. So if I wanted to get an epsilon approximation, 1 plus epsilon approximation with constant probability, how many samples do I need? Yeah, I mean 1 over epsilon squared times this probability, or if you want to substitute some other delta. I did delta over 2 because there's another side, right? You want to upper bound, you want to lower bound it. Okay? That's wrong. So actually the whole point of this slide is that this needs to be in the denominator. Okay? Something like this. Okay. So it needs to be inversely proportional to this probability you're sampling. Okay? Real problem is that if that number was really close to 0, it's going to be a hard time to tell the difference between 0 and something very close to 0. Okay. So here's another problem. This is a problem we're actually going to focus on today. Okay, so something like SAT, except it's disjunctive normal form. So instead of and of ors, it's an or of ands. Okay, so you can satisfy this formula by satisfying the first clause, or satisfying the second clause, or satisfying the third clause, or so on and so forth. Okay? And the question is not whether it can be satisfied. That's easy. You just look at a clause and see if x1 and x1 not appear in it or something, right? But how many assignments satisfy this clause? It could be a very big number. It could be a very small number. Okay. So that's our goal. We want to estimate this. Okay. How might we go about this? I can try randomly sampling and seeing if it satisfies, right? And seeing the probability of a random assignment. And then I can scale that up by 2 to the n. So, sorry. Okay, so we can look at this probability of it being true will be the number of satisfying assignments divided by 2 to the n. So we'll set up a bunch of random variables, one for each random assignment, one if it's true, zero otherwise, right? Okay, so now how many samples will we need? So if I called this mu, okay, then that n should be a k again, but probability of being too big by say 5% is going to be like e to the negative epsilon squared mu k over 2 or something, right? So how big should k be then? Like what? What should k be to get that thing down to, at most delta, or at most 1/2 even? Yeah. So the problem is that you need k to be something on the order of 1 over epsilon squared mu. But in this case, mu can be as small as 1 over 2 to the n. Okay, so it's not as obvious how to sample and figure out this value. So, okay. So, we're doing some kind of like mean estimation style problem, okay, where, you're trying to figure out the average of this variable and it's bounded or something. And your goal is to estimate, the goal is to estimate the value, and you assume you have access to independent samples. And if you just take the direct, Chernoff style approach, then let's see what's written here. Just sample a bunch and return the average. You're going to find that you need to do something inversely proportional to the actual average to get a multiplicative approximation. It's just really hard to tell apart zero from really close to zero. Okay. So the first point is this is a good approach for many situations, this sort of Monte Carlo kind of thing. It's fine for estimating the area of a circle. But we're going to focus on interesting situations where this can be really small, but maybe you can still be clever and come up with something. Okay. So, okay. Okay, so this was our initial idea. It didn't quite work because mu could be so small that we can't directly apply Chernoff and get something useful. So, any ideas for what we can do instead? Okay, so maybe I'll start with a satisfying assignment and then flip some of them and see if it's still satisfying. Oh, okay, that's an interesting idea. Um, uh, uh, that's not a bad idea, though, but it won't ultimately be what we do. Yeah. Yeah. Okay, I can try to do inclusion exclusion. So what would the algorithm do first? Ah, okay. So one thing to keep in mind is that even if there was 2 to the square root n satisfying assignments, that's a big number, but mu is still very small because it's 2 to the negative square root n. So anything that approaches enumeration is going to be tough. You might be able to try to sample, or maybe if you want to estimate the inclusion, what was the overlap of two clauses, you can try, on average, you can try choosing two random ones, right? That's not a bad idea, but it's not quite the direction we're going to go. But so inclusion, exclusion, right? Like you're worried about the overlap. So okay, I can count each. So one thing nice is I can count each clause separately. So if a clause has like 10 variables, there should be like 2 to the n minus 10 satisfying assignments because those 10 variables are fixed and everything else can be anything. So you can count each one separately. Then you have to worry about the overlap. So let's figure out, for every two clauses, which ones are in that pairwise overlap, which I guess means you would concatenate the two clauses and you get 2 to the n minus something. So maybe you're not enumerating. Then you have to figure out intersection of 3, and then intersections of 4, intersections of 5. I guess maybe actually you can calculate things explicitly because it's going to be 2 to the n minus after combining the clauses. But maybe the more bigger issue is that you have so many clauses that this will quickly get. It's not clear how far up you have to go. Um, yeah. Okay, let me try giving you a hint though. So eventual solution is going to be so slick the lecture is going to finish faster than you realize. So I'm going to try to give hints to see where along the way you stop me. So okay, so first, sort of building off this idea, I'm going to let S sub I be the set of assignments that satisfies a particular clause I. Okay, in which case uh, the number of these is the number of n minus the number of variables in clause I. Okay, is that very helpful? Probably not. Let's see if there's anything here. So I'm trying to estimate the size of the union, right? Because I just need to satisfy one of the clauses. So the issue is dealing with all these overlaps, right? Yeah. Yeah, we want a multiplicative approximation. Yeah, so additive would be easier. You would just, for epsilon additive, you need like 1 over epsilon squared samples if I plug that in correctly. Um, and yeah, but in general in computer science, we often want to do things that are scale invariant, right? So multiplicative approximations usually are what we want, except for some situations where I guess yeah, like epsilon net, it's not always the case, but okay. So that's one hint. I suppose this doesn't inspire anything yet. Well, so I think we're still going to treat this as sort of the numerator of our sampling, but now consider this. Okay. Let me first point out, so this quantity is, the numerator is what we're looking for, divided by the sum of different ones, okay? Let me point out some things that are convenient about it. The numerator is what we want, of course, that's convenient. The denominator, we at least can do the math, right? We can add this up and figure out what the denominator is. So if you can estimate mu up to 10%, then you estimate the numerator up to 10% because you can just clear the denominator. So that's great. Now, what else do we know about mu? What's like a lower bound on mu? Because we want mu to be high, right? Or moderately high. 1 over m. Because each thing in the numerator, each assignment can only appear in all of them, which is m of them. So, of course, that seems small, but it's much better than 1 over 2 to the n, right? If we're just trying to get things that run in polynomial time, this is fine. So we're making some progress. Now, if I can think of an experiment where I'm kind of sampling from the denominator and then sort of identifying the numerator, right? Then we would be done. Yeah, what should I do? Okay, so I'll sample one of these. Like I'll sample S2 with weight proportional to the number of assignments in S2, and then, so okay, so far I've just sampled one index, right? Check if the clause is in the numerator. What's the whole algorithm? So if step one of the algorithm you guys are describing is I choose one clause in proportion to the number of assignments in it, in proportion to the size of SI. So I've chosen a clause. I've chosen clause one. What's the next step? Okay, I'll choose one assignment inside. So I can now interpret the denominator as number of combinations of a clause and an assignment in that clause. So I have an index I and I have an assignment. So we have an interpretation for the denominator. What about the numerator? But a numerator it doesn't describe, that would be S1 and S2 and S3 and S4, right? Instead, we're looking at S1 or S2. So now comes maybe the trickiest part, trying to figure out some way to describe the numerator and turn this into a yes or no kind of thing. So if I can come up with a procedure that sort of, I want to estimate mu because I know how to calculate the denominator. I know that mu is also a large enough number that I can live with it. And if I can come up with an experiment where it's true with probability mu and false with probability 1 minus mu, and I can estimate mu. So the first step of, so at some level, we're trying to interpret the denominator as something you're sampling out of, and the numerator is sort of that bullseye target. Is it in the bullseye, right? Is it in the circle? So we can interpret or identify the denominator as a choice of a clause and an assignment satisfying that clause. So it's sort of like tuple. So indexed assignments, I guess. Yeah, now what about numerator? Remember, the real thing is that this, all the assignments appear here, but assignments that appear multiple times, only count for one. Okay, so our algorithm, okay, so we're going to try to come up with some procedure where it's in or not, or true or false. We want the average to be mu. And if we can define this, then I just have to repeat the sample like roughly 1 over m times, or roughly m times, m over epsilon squared to get 1 plus or minus epsilon. So what's the full procedure? Right now, I think we have a reasonable candidate of what I sample. So now you sort of figure out how to sample from the bounding box. Now we have to define what it means to be in the circle, the area of the thing we're trying to estimate. So if the assignment doesn't satisfy anything else, then it only appears as multiplicity 1 in the numerator, so that's great. But the interesting case is, okay, this assignment is in 5 of the clauses or something, right? So, and if I just said, oh, it satisfies the clause, I'll be counting it 5 times as much as I should be or something, right? So we need to do something clever. Oh, we can try to divide by the number of clauses it's in. So I can look at an assignment and say, oh, it's in 10, so I'll output 1 over 10. think that'll actually work. It's actually not what I had in mind and not what the textbook had in mind. By which I, not just my textbook, other textbooks. Um, I think that'll work. Uh, so okay, does that make sense? So I'll sample something for the denominator. If it's in five of the SIs, I'll output 1/5. Well, we just have to analyze the expected value. Um, yeah, let's try. Let's see if we can pull off the calculation. Uh, yeah, what's down here? Okay. So that's useless. Let me erase this. Um, okay, so let's look at that experiment we just came up with, which is a little different than what we'll eventually do, but maybe this is just as good. So the idea is I'm going to sample one clause and one assignment from it, and then I'll output 1 divided by a number of clauses that contain it. Okay, and so that would give me some variable. I'll call it x or something, right? Or maybe there's already x. I'll call it z. Okay, so z is equal to 1 divided by the number of satisfy clauses satisfied by our assignment thingy. Okay. Okay. So now the question is, what is the expected value of z? Yeah. 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 In SI. Yeah. So we sample the index I, and then we sample x in SI uniformly, and then we'll divide by number of clauses satisfied. Sorry. Sorry. Yeah. Yeah. Sorry. You satisfy. Yes. Yeah. Yeah. The first step is not uniform. So you're really sampling a satisfying assignment with repetition from like the multi-set of assignments in this uniformly at random, which we just break down into two steps, figure out the set I first, the index I, and then, yeah. Yeah, so we can break it down. So if we sum over all the clauses 1 to m, and with probability 1 over si, I sampled this thing, right? And then, we sum over, I guess, all of the assignments x and si, 1 over number of clauses for x, I guess I'll just write, I'm just, okay. Times 1 over, okay, so this is wrong. The first part's wrong, right? Sorry, this should be, size of si divided by, I'll just write d for denominator, okay? So, okay, so these things cancel out, and now we have 1 over d, summing, and I'm going to interchange sums, summing over all the x's, all the possible, I guess, x and d. Um, and you have 1 divided by the number of clauses containing x, times, I guess, summing over all the sets I containing x, 1. Oh, is this getting us something useful? Okay, good. So I'll write x and n for numerator. Okay. And now we see that every single thing in the numerator, which is one satisfying assignment, um, right, because only those are only ones that will appear somewhere down here. Uh, and then each one is giving this 1 over number of clauses that it satisfies term and appears one time for every clause satisfying it. So these two will cancel out and you'll get n over d. Okay, so that'll work. And Chernoff doesn't care if it's 0, 1 or between 0 and 1. And our thing is between 0 and 1. Okay, so good, we're done. No. I'll only mention, well, the way people used to do it. Did I write it down? Well, if I didn't write it down, then I don't have to mention it. Well, okay, so the other way you can do this, and it'll lead to similar calculation so you choose your index I and you sample X just like that. Then you look at X and you say, is this the first index I containing X? So if there's 10 clauses, only if it's in the first of the 10, you get 1. Otherwise, you do 0. On average, they'll give you 1 over 10, so it'll kind of work out similarly to what we do. Okay, so that's the version in the notes. Okay. Which is better? I don't know. I kind of like our version. I think it's a good idea. Yeah, but that version makes sense too. Okay, so that's one of our two topics for today then. Any questions? Here. So I sample X and SI. So our thing samples it was probability 1 over SI. And then the value you get is, this is Z. So I interchange sums. So now I'm looking at all X in the numerator because it has to appear in at least one SI. And then here's that same term. And then there's one of them for each SI containing X, and that's the same thing. Any other questions? Okay, I should mention there's many other kind of interesting problems, like trying to estimate how many perfect matchings are in a bipartite graph. Okay, there could be many. And this is a starting point, but there's a few more tools we need. So we might come back to it later because you need a little bit of kind of analyzing a certain kind of random walk. But so there's a lot more significant results, but they're all building on this kind of, I want to do sampling, mu is too small, so I have to somehow understand a little bit about the structure and do something smarter. This is sort of this is sort of the starting canonical example.